So 11.7 is where we are today, and we're going to talk about area and volume ratios. So what we're talking about today is similar solids. So the first thing we need to know is, how do we know when solids are similar? Well, what's one thing that we know for sure it has to be true about these solids for them to be similar? They have to be the same shape, right? We can't have a sphere be similar to a cone. They have to be the same shape. So if you were talking about a polyhedron, they have to have the same number of sides. They have to have the same configuration. So they have to be the same shape. So to be similar, they have to have the same shape. And the other thing we talked about with similarity is we compared sides. So I'm going to say they have to be the same shape, and I'm going to say all corresponding dimensions are. And what happened when we compared the corresponding parts of similar shapes? What did we use to compare them? Our big tool. What's that? A scale factor? So a scale factor was another way of saying they were. What was our big tool when we worked with similar figures? Not congruent, but proportional. There we go. All corresponding dimensions are proportional. So when we're talking about similarity, we're talking about proportions. So if we match up the corresponding dimensions of similar figures, they're going to be proportional. So if we're talking about a polyhedron, we would match up the corresponding sides. Short with short, medium with the medium, long with the long. They'd all be proportional. They would all have the same ratio. And then if we're talking about other kinds of shapes, we can match up other dimensions. So if we talked about cones, we could match up the slant heights and the heights, and those would be proportional between similar cones. So let's look at a couple of examples, and we're going to decide whether or not these things are these things are proportional. We'll start with a couple of boxes. So there's one, and here's my other one. And I said these were boxes. What was our mathematical way of saying box? Rectangular prism. So we have two rectangular prisms. And I'm going to say this is 8, 3. The dimensions here are 8, 3, and 5. And 10, 4, and 7. And we want to know, are they similar? So to decide if they're similar, we have to match corresponding sides. If you have a question, we just stretch. Okay. So on the smaller prism, what are we going to match with the 8? The 10. So 8 is the biggest side. We're going to match the big side with the big side. 8 over 10, and that will reduce to 4/5. And we would have to have the same ratio for all the corresponding sides for this to be similar. So what side are we going to match with the 3? 4? 3 over 4? Is 3 over 4 the same as 4/5? No. 3 over 4 does not equal 4/5, so our answer would be no. Not similar. If the second one turned out to be the same, then we would have to make sure the third one worked out the same as well. So let's look at another example. So here are my boxes, my rectangular prisms. So this made me think of I had a question. If someone asked, if you're talking about boxes, and someone asks you, oh, I need a box that's twice as large, what could they be asking? I was just thinking about how that's not necessarily a good question. Right, we could want double the volume. We could want it to be the scale factor to be 2. So that's not necessarily, because if our scale factor is 2, our volume is going to be more than twice as large. That just popped into my head. All right, so that's 10. We're going to say that's 4, and that's 6. And we're going to say, and I know it doesn't look that way on my drawing, that's 15. This one maybe is further away, 6. And 9, we're dealing with perspective. And we want to know, are these similar? All right, so we're going to match up our corresponding sides and make ratios and make sure they're all the same. So what are we going to match up with the 10 here? 10 over 15. And we can reduce that to what? Divide by, what's the biggest number that divides into both of those? 5 divided by 5, so I get 2/3. What am I going to match up with the 4? 6. That's the small side, so I get 4 over 6, and I divide by 2, and I get 2/3. And the last side, 6 over 9. Got to check all 3. 6 over 9, and I can divide by 2. And I get 2, or divide by 3, and I get 2/3. They're all the same, so this would be yes. They are similar, because all the corresponding dimensions are proportional. All right, so what we're interested in here, questions on this? How we did this? Okay. So what we're interested in is not necessarily deciding if our solids are similar, but we want to use the idea that we have a similar solid to solve problems. Before I go on, I want to ask, what kind of shapes would always be similar? 3 dimensions? Cubes. So 2 cubes always going to be similar because we're just multiplying. There's only one dimension that we have to compare. What other shape? Sphere. Spheres are always going to be similar because they're always the same shape. All we're doing is multiplying the radius by something to get another. So those two are nice because they're always going to be similar. All right. So what we're interested in is if we have similar figures, how do their areas and volumes compare? So that's really what we're interested in. How do we work with their areas and volumes if they're similar? So we're going to say if the scale factor and the other way we said the scale factor, the other way we used it before, and I'm just going to go back here really quickly. The scale factor is the ratio of the sides. So we called the scale factor, the other word for it, the other way we talked about it was the length ratio. If the scale factor, the length ratio for similar solids is A over B. The area ratio And we talked about this one last chapter. If we have our scale factor, how do we find the area ratio from the scale factor? Square it. The area ratio is a squared over b squared. And because we're talking about solids, we're talking about surface area. We're talking about the surface area. But we're still talking about area. The volume ratio is, what are we going to guess we do to the scale factor to get our volume ratio? Cube it. And our ratios go with our dimensions, our units. So length, we just talked about inches, meters, whatever. Volume, we talked about square inches, square meters. We're squaring it. Volume, we talked about cubic inches, cubic meters. We're cubing. So if we have the length ratio, we can find the area ratio and the volume ratio. We can use that to solve problems. If we have the volume ratio, what do we do to get to the length ratio? They go from the cubed to the not cubed. What do we do when we solved that problem with the sphere the other day? When we had r cubed equal something? Cube root. We take the cube root. So to go backwards from the volume ratio, we can take the cube root to get to the scale factor or the length ratio. And if we have the area ratio, because these are both squared, we want to get back to just a over b, we take the square root. So we can work these problems in both directions. And one thing that I want to point out is our length ratio, our scale factor. And I'm going to put in parentheses our length ratio again. Our length ratio can be the ratio of any corresponding length. So I could talk about the ratio of the perimeters. I could talk about the ratio of the slant heights. I could talk about the ratio of the circumferences. I could talk about the ratio of the radii. So the scale factor, our length ratio, can be the ratio of any corresponding length. So it doesn't just have to be a side. We can make a ratio of any corresponding length. As long as it's a length ratio, it's going to be the same as our scale factor. So sometimes they'll ask about perimeters or circumferences or slant heights, and it's not necessarily a side. Doesn't matter. Still a length ratio. All right, so let's use this idea to solve some problems. These are very much like problems we solved in chapter 10 when we were talking about area. Okay. So we're going to have two solids here. So this looks kind of starting out kind of like our last couple of problems. And we know the volumes of these two. We know a couple of things about these things. We're going to know their volumes, and we're going to be told that they are similar. So the volume of this solid is 3375 cubic units. And the volume of this solid is 1728 cubic units. And we want to know what is the scale factor. And I'm going to say of the similar solids. So the problem tells us they're similar. We want to know the scale factor. So what can we do with these two volumes? Yes.
That's a unit squared.
Oh, this should be units cubed. Thank you. So what can we do with these two volumes? Make a ratio. We're going to write the volume ratio. The volume ratio equals 3375 over 1728. And our volume ratio we know is a cubed over b cubed, where a over b is a scale factor. So how do I get from the volume ratio to a over b? What do I do to get from the volume ratio to the scale factor? Cube root. So I'm going to use the cube root. So a over b, our scale factor, is the cube root of 3375 divided by the cube root of 1728. And let's remember how to do that on our calculator. Let me get this one up. Just as a reminder how to calculate cube roots. If you need help making sure you know how to do this on your calculator, just let me know and I can help you out. So our cube root, I'm going to do a 3, and then I'm going to use this little button that says x and then the square root sign. That's telling me I'm doing the cube root. The cube root of 3375, and the calculator tells me that's 15. And then I do the cube root of 1728, and the calculator tells me that's 12. So our scale factor is going to be 15 over 12. And can I reduce that to 5/4? It doesn't matter. Sometimes the problem will say the scale factor larger to smaller, or scale factor smaller to larger. Here we didn't say, so it doesn't matter which one. Just as long as we keep the big volume should go with the big length ratio. So don't switch them around in the middle. All right, questions on how we found that scale factor? All right, this process is going to be important for our next problem because we're going to add one more layer to our problem. Okay. So this problem says the volumes of two similar solids are 40 cubic inches and 135 cubic inches. The surface area of the smaller is 48 square inches. Find the surface area of the larger. Folks, electronics, put them away, please. Surface area of the smaller is 48 square inches. We want the surface area of the larger. All right, so what are we going to do here? Well, we have two volumes. So, using our last problem as a starting point, what can we do with the two volumes? Use the two volumes to find the scale factor. So our plan. So we're going to use the volume to find the scale factor. We can use the scale factor. The problem asks us about the surface area. So use the scale factor. What will the scale factor? What can we do from the scale factor to have something to do with the areas? Let's go back here. If we have the scale factor, we can square it to find the area ratio. So we're going to use the scale factor to find the area ratio. And then finally, our third step is write a proportion with the information that the problem gives us to find the missing volume. And we're looking for a missing area. So let's use the volumes to find the scale factor. We want the surface area of the larger, so I'm going to write my ratios with the larger over the smaller. So our volume ratio, so here's for step 1. Our volume ratio is 135 over 140. Just 40, thank you. Our scale factor, how do we find our scale factor from the volume ratio? What do? Cube root. Scale factor is going to be the cube root of 135 over the cube root of 40. When I calculate that in my calculator, when I put that in my calculator, I get 5.13 divided by 3.42. So I just put cube root of 135, found that in my calculator, that's 5.13. Cube root of 40 in my calculator, 3.42. So there's step 1. We found our scale factor. Use the scale factor, or step 2 is use the scale factor to find the area ratio. Area ratio from the scale factor, what do I do? What is it? Square it, there we go. We're going to square it. The area ratio is going to be 5.13 squared over 3.42 squared. Plug that in my calculator, square 5.13, and I get 26.32. Square 3.42, and I get 11.7. So there's my area ratio. Now we can solve the problem. Let's call the surface area of the larger solid X. So I'm going to write an area ratio using the part that we're looking for and the information that the problem gave us. So our area ratio is X over 48. And that has to equal the area ratio we get from squaring the scale factor. That equals 26.32 over 11.7. And then to solve this, I cross multiply. All I need to do is multiply both sides by 48. So X equals 48 times 26.32 over 11.7. I plug that in my calculator, 26.32 divided by 11.7, multiply by 48, and I get, rounded to the nearest square inch, I get 108 square inches. So the surface area of the larger solid would be 108 square inches. So the key to this problem was to find the scale factor. From the scale factor I can find any of the ratios that I want. And then I use the information in the problem to write another fraction that also represented, that also gave us the area ratio. The area ratio is the area of the larger over the area of the smaller. That's also the area ratio that we got from squaring the scale factor. And then I can solve this by cross multiplying. Yes?
Where did you get
The problem said that the surface area of the smaller is 48 square inches. So it told us that. And we were trying to find the surface area of the larger, so I call the surface area of the larger one x. Questions there? All right, let's look at one more example similar to this one to look at this process one more time. The surface area of two similar solids surface areas, I guess, are 52 square feet and 208 square feet. The volume of the larger is 192 cubic feet. Find the volume of the smaller. So this is almost the exact same problem, except we're starting with the surface areas. So our procedure here is going to be use the area ratio to find the scale factor. Use the scale factor, find the volume ratio, write a proportion using the information that the problem gives us. So our area ratio. Our area ratio, and since we're looking for the volume of the smaller, I'm going to put the ratio as smaller to larger. Our area ratio equals 52 over 208. Our scale factor. How do we go from the area ratio to the scale factor? Area ratio is squared. Scale factor is not squared. So how do I undo a square? Square root. So square root both of those to get to my scale factor. Square root of 52 is 7.21. Square root of 208 is 14.42. Anybody see anything interesting about those two numbers? One half. If I double 7.21, I get 14.42. My scale factor is 1/2. My volume ratio is 1/2, and we're going to cube each of those. 1 to the third over 2 to the third. 1 to the third is just 1 times 1 times 1. We get 1. 2 to the third is 2 times 2 times 2. 8. The volume ratio is 1/8. if we call the volume of the smaller x, so our volume ratio also equals x over 192. From the problem, we can make the volume ratio from the information they give us in the problem. X, one we want to know, 192 is the one the problem tells us. And that has to equal 1/8. This is my volume ratio, this is my volume ratio. They're the same thing. Cross multiply here, so I'm going to multiply by 192. So x equals 192 times 1/8, which is the same as dividing 192 by 8. So x equals 24 cubic feet. Now a couple of ways that you can check your work here. We were finding the volume of the smaller solid. If our volume turned out bigger than the volume of the big solid, we would know we'd made a mistake. You have to get a smaller volume than the solid. So that's the way we check our work. Same thing we did over here. We were looking for the surface area of the larger. It has to turn out bigger than the surface area of the small one. Well, the surface area of the small one is 48. So if we got something smaller than 48, this is the larger solid, we would know that we made some kind of mistake. All right, questions there? So this is really the key to this section, is using your scale factors, using your ratios to find other pieces of information. And this is exactly like what we did with our area ratios in chapter 10 with similar shapes. Okay. Homework, page 746, number 6 through 28, even. For the test, I'm not going to give a formal review assignment. I'm going to give you some suggestions for preparing for the test. So my suggestions are suggested review problems. Page 752. Suggested review. So for the review, what you should do is make sure you know how to use these surface area volume formulas for different shapes, different kinds of bases. Make sure you can figure out what's the base, what's the height, what's the slant height, what's the area of the base. So suggested review, page 752, number 4 through, there's a lot here, 35. So you have a lot of problems to pick from to use your formulas. You could also look at page 755, number 6 through 14. You could also, in your power geometry, your online textbook, your lesson quizzes, so in each section of chapter 10, chapter 11, sorry, each section of chapter 11, after the section, it has a lesson quiz. So you go to the lesson quiz for section 10.2, and you can take that little lesson quiz to see if you understand the topics in that section. So you can go to the sections of the chapter and do the lesson quizzes. And I think is it in the to-do? This might be in the to-do. But there's a lesson quiz after each section in the online textbook. So working through some of these problems to make sure you know how to use these formulas is going to be good practice. So this is the homework. I'm not going to collect these. This is not an assignment. but this is how you should work on preparing for the test. Best way to prepare for a math test is do more math problems. All right.